Imagine an AI that doesn't just talk to you like ChatGPT, but actually designs new medicines and helps decide where we build the power grid of the future. In this video, we're going to look at two real breakthroughs that quietly mark a turning point for artificial intelligence. First, a generative model from MIT called BoltzGen that can design protein binders, molecules that latch onto specific biological targets directly in silico. Not just predicting structures, but inventing brand new candidates that could one day become drugs. Second, a wave of AI systems being tested and deployed to plan and operate cleaner, smarter power grids. These tools don't just forecast demand, they help plan new lines, size batteries, and even suggest how to react to sudden surges in real time. Together, they tell a bigger story. AI is moving from language and images into the physical world, into biology and into energy infrastructure. Let's break down what's actually happening, what's hype, and what it could mean for the next decade. Most people still think of AI as chatbots, image generators, or maybe deepfakes. But the systems we'll talk about today work on a different layer. They operate on the rules of physics, chemistry, and electricity. Instead of generating sentences, they generate candidate molecules that must obey thermodynamics and atomic geometry. Instead of generating pretty pictures, they generate grid plans and control actions that must obey Kirchhoff's laws and keep the lights on. That shift from symbols to the underlying physical constraints is what makes these advances so interesting. Because if AI can reliably reason with those constraints, then it might become a design partner for things we care about most: health, climate, and critical infrastructure. Let's start with the biology side. In November 2025, a team from MIT's Jameel Clinic, CSIL, and collaborators introduced BoltzGen, an all-atom generative model for designing proteins and peptides. BoltzGen doesn't just guess what shape a protein will fold into. It unifies three things in one model: structure prediction, binding site modeling, and sequence generation. In simple terms, you give it a target, say a disease-related protein you want to block, and BoltzGen proposes entirely new protein binders that should fold correctly and stick to that target with high affinity. Why is this a big deal? Traditionally, discovering a new drug candidate is slow, expensive, and incredibly wasteful. You might screen millions of existing molecules in a wet lab or via docking simulations, hoping a tiny fraction shows promise. Models like BoltzGen attack the problem from the other side. Instead of searching randomly through chemical space, they generate candidates that are already biased toward good structure and good binding. According to the MIT team, BoltzGen operates at the all-atom level and has been validated on diverse targets, showing strong performance in producing realistic, physically plausible binders. But that doesn't mean every output is a future medicine. You still have to synthesize the protein, test it in cells, run animal studies, and eventually clinical trials. Biology is messy, and AI can't shortcut safety. But it does massively change the front end of the pipeline. Instead of a human medicinal chemist brainstorming a handful of variants, you can ask an AI for thousands of candidates tailored to the exact geometry and chemistry of your target. You can also add constraints. BoltzGen supports a design specification language. You can specify certain covalent bonds, structural motifs, or binding site features you want to enforce. That means the model isn't just hallucinating random shapes. You can steer it toward particular classes of molecules or away from sequences that look risky or unstable. It's tempting to jump to AI just solved drug discovery. That's not what this result means. Right now, these are candidate binders, not approved drugs. The success rate when moving from in silico design to real biological effect is still uncertain. Many downstream constraints, toxicity, immune response, manufacturability, aren't fully captured in the model. So a truthful way to think about BoltzGen is this: it's a new kind of searchlight in a dark chemical universe. It points us to promising regions that would have been very hard or impossible to find manually, but we still have to walk there, test them, and see which paths actually lead to useful therapies. If you're building in AI or biotech, that's the pattern to watch. Models that don't replace experimental science, but radically compress the idea generation and hypothesis phases. Now let's shift to the second story. AI for clean energy and power grids. Modern electric grids are becoming much harder to manage. We're plugging in intermittent renewables like wind and solar, adding millions of electric vehicles, and dealing with more extreme weather events. Grid operators and planners are being asked to juggle reliability, cost and decarbonisation targets all at once. That's where AI is starting to show up in three main areas. First, operations and control. AI models can analyse data from sensors, smart meters and substations to suggest real-time control actions, like changing voltage settings, rerouting power or dispatching storage to keep the grid stable and reduce losses. Second, planning and investment. AI tools help planners design future grids under deep uncertainty. Researchers from places like MIT and the National Renewable Energy Laboratory use models that simulate future demand, renewable output and extreme events. These systems recommend where to build new lines, where to place batteries and how to meet clean energy targets. Third, forecasting. Machine learning dramatically improves predictions of solar and wind output, reducing the need for costly backup energy and helping operators integrate renewables without losing stability. And this isn't just theory. Utilities in places like Brazil, India and parts of the US are already deploying AI systems to detect failures, manage load and predict spikes before they happen. So what does it actually mean for AI to plan a power grid? Let's break it down. You have a map of where people live and use electricity. You have existing lines, substations and power plants. You have predictions for new wind farms, solar farms and the rise of electric vehicles. You have policies about reliability, emissions and cost. The planning problem is simple to state, but brutally hard to solve. What should we build? Where and when? So we can meet demand reliably, minimise costs and hit climate goals. Traditionally, planners run huge optimisation models one scenario at a time. But with renewables and changing weather patterns, the number of possible futures is exploding. AI helps by learning fast approximations of grid behaviour, called surrogate models, and by generating thousands of realistic futures so planners can build resilient designs that hold up under many possibilities. What's fascinating is how similar the molecule problem and the grid problem actually are. In both cases, AI explores a massive search space. In both cases, physics imposes strict rules. And in both cases, the stakes are high. Getting things wrong can affect lives, infrastructure and safety. And in both cases, the future is not AI replacing experts. It's AI becoming a design partner, generating ideas humans could never reach manually. There are still limitations. In drug design, AI doesn't predict toxicity, immune response, or manufacturability perfectly. In grid design, AI introduces new failure modes, security risks, and governance questions. Neither field is solved, and both rely heavily on human oversight. AI is powerful, but context, safety, and judgment still belong to humans. Zoom out, and these breakthroughs show a new phase of AI. AI isn't just generating content, it's helping design matter, energy systems, and potentially the infrastructure that shapes society. That doesn't mean AI labs will replace pharmaceutical companies or utilities. But it does mean AI literacy will become essential in biology, chemistry, and power engineering. Collaboration across fields will become the norm. We've explored an AI that designs protein binders and AI systems that help plan the energy grids of the future. Both breakthroughs are early. Both need validation and oversight. But together, they show a future where AI becomes a trusted partner in the labs and control rooms that shape our world. If you enjoyed this deep dive and want more content about real AI breakthroughs, not just chatbots, hit subscribe and tell me which topic you want the next episode to explore.